Hi, I'm Ben-Yaakov. This presentation is entitled Google's Switched Tank Converters. There are some relevant videos to this presentation. Here are the links, and I'm going to print the link to the description section of the video that you are now watching. Now, around 2018, Google sort of surprised the power electronic community by this patent and some papers that were accompanying it. In that, they discussed an application of a switched tank converter, which is basically a switched capacitor converter. It's a resonant switched capacitor converter. And the reason for the surprise was that up to that point, switched capacitor converters were considered, first of all, something like a curiosity, and then they were considered to be suitable for low power. And here Google shows that you can use it for high power at high efficiency, and it could be useful in a number of very key applications. So the purpose of this presentation is, first of all, to talk about the objective of this circuit that was presented by Google, talk about switched capacitor converters as an introduction to understand what is this technology all about, talk about losses, which are the key issue here, and then talk about resonant switched capacitor converter, because the converter that Google is showing is basically a resonant switched capacitor converter. And then I'm going to discuss how does the Google switched tank converter work, and that is the inner working and the different mode of operation. So what is the objective of this circuit that was proposed by Google? It is supposed to be like an intermediate power supply. Here I'm showing like a system which has a line input, power factor correction, and then DC to DC. And then it might have a bus, say 48 volt. This will be like a server. And then there will be an intermediate DC to DC converter to bring it down to, say, 12 volts. So it'll be more practical to get by DC to DC, the lower voltages, 5 volt, 3.3, 1.1, etc. So this is an intermediate DC to DC converter. In this particular case, it's a 4 to 1. And what is really nice about it in terms of the requirement is that it doesn't have to be regulated. That is, it has to have a certain voltage transfer ratio. But if this voltage, 12 volt here, is changing, it doesn't matter because there are regulator DC to DC converters here. So what it has to do is to have a step down, high power, and of course, high efficiency. So as an introduction to the whole issue of switched capacitor converters, I'm starting here with a simple converter, which is a 2 to 1 ratio, to explain how it works, because for those who are not familiar with switched capacitor converters, the whole issue might look a little bit mysterious. So I'm starting with the very, very basic. So even those who don't have a prior knowledge of switched capacitor converter will be able to understand this Google's circuit. So this is, as I've said, a 2 to 1 ratio step down DC to DC converter. I'm showing here switches. Obviously, they're going to be MOSFETs. And here is an input, here is the output. And in order to analyze this, in this particular case, it's the best way to start actually from the output going back to the input, and this is what I'm going to do. So starting with this step here, we have these two switches on, S2 and S2. And in here, we see that the flying capacitor, the so-called flying capacitor, is connected to the output. I'm assuming steady state, there is a voltage here. So the capacitor voltage will, after a while, will be equal to the output voltage. And then by the other two switches, S1 and S2, we are connecting actually the input to the output via the flying capacitor in such a polarity that the output here is basically V in minus the voltage on the capacitor, which is V out, and therefore V out is V in over 2 in the steady state. Okay, so obviously we have here a way of getting a voltage which is a certain ratio of the input. In this particular case, it's a step down. But if this capacitor would have been connected in series in the polarity that is added to the Vin, then we would have had a step up. So it could be used for step down, step up. And with the proper topology, you can get, of course, many ratios rather than this 2 to 1 that I'm showing here. And now, what about the charging and discharging of this capacitor? Let's start from here. When this capacitor is connected in series here, to get here actually a V out, V in minus the capacitor voltage is actually V out, you see that in this case the path is charging this capacitor. Okay, so the capacitor in this stage is being charged, while in this stage, when it is connected in parallel to the output, it is being discharged. And the nice thing about this particular converter, which is not always the case in switched capacitor converter, that you have actually current, continuous current pumping into the output. To demonstrate what is really going on, I've set up here a LT-Spice circuit. I have here 4 transistors now instead of these switches. This is the flying capacitor. This is the output section. And I have here, of course, programmed the pulses here. It's a 2 megahertz switching frequency. It's a duty cycle of 50%. And then we have the 2 switches working together, as I've shown it earlier. And here is what I'm getting. Now, these are the control signal for the switches, for the MOSFETs. Okay. Here we see the charging of the capacitor and discharging. This is the voltage across the capacitor, and this is the output. Now, this is, of course, zoomed very much, so we see here millivolts here, and the voltage is pretty close to 2.5, which is half the input voltage. And this is just for demonstration, of course. It has no special meaning, the values here. So as I've said, the central issue of a converter like this switch capacitor converter is the loss, the issue of loss. That is, you can use it to high power if the loss will be low, so you can get a high efficiency. So I'm going to go over the issue of losses. Again, I'm limited by time, so I'm not going to repeat the whole derivation. They are found in the video that I've referenced. I'm just going to give here the actually end results that we'll use it later on for understanding the circuits on hand. So if I have a switch capacitor converter, it will have cells which look like that. That is, it could have many of these, but basically we're going to have a capacitor which is switched on one side to a voltage, or a capacitor, a large capacitance capacitor, and to a voltage again, or a capacitor. This is the basic cell, and again could be a number of them, like we have seen here. We had actually 2 cells like this here. So the question, what are the losses here? Now, the losses are due to currents which are passing through these parasitic resistances. This is the only reason for the losses. Now, when you charge and discharge a capacitor like this, then obviously you're going to have a charging current, a discharging current, and I'm showing here different shapes depending on the time constant. If the time constant is short relative to the on time of the switch, then you're going to have a spike here, and then it'll go down very quickly. And then if the time constant is moderate, it will be something like that. And if the time constant is very long, you're going to have just about a straight line here. Okay, so this is just a question of what is the time constant compared to the on time. Now, in this presentation, I'm not going to derive all the results related to losses, just to summarize the end result. And whoever is interested should look up the videos that I've referenced. Now, as it turns out, we can represent a system like this, like you might say, a Thevenin equivalent circuit with a voltage source and an internal resistance. Now, this is the target voltage. Now, in the previous case, it was half of the input voltage. RA actually represent the losses. The larger the losses, the larger will be this resistance. Now we can understand now that if we load it, then there will be a drop, and consequently there will be a lower voltage at the output and losses here. And this is very similar to an LDO. Now, a very important characteristic of this circuit is that the equivalent resistance has this shape, this curve here. Now, this is the resistance, and this is the frequency, and this is in a log-log scale. Now, we have here a portion in which the equivalent resistance is 1 over Fc. F is the switching frequency, C is the flying capacitor, this one here. Okay, so it goes down until it reaches this region here, which the time constant is long, and eventually it is like straight line here. And then Ra is basically the actual resistances, because then if you are in this region or in this region here, then you have a DC current, you might say, passing through these resistors. So the RMS and DC are the same. RMS here of these shapes is much higher than the DC value, and therefore you get a more losses, because the losses of course are a function of the RMS square, the RMS current square, and therefore you have this shape here. So let's take an example here. Suppose the switching frequency is 1 megahertz, the on time is 0.5 microsecond, the duty cycle of 0.5, and let's assume that we have a value of the RDS on and the ESR combined something like 10 milliohms, it's practical. And then we know that the equivalent resistance is 1 over Fc, F is 1 megahertz, C is 10 to the minus 6, 1 ohm. So you see that the resistance, equivalent resistance, is much, much higher than the original resistance in the circuit. And this is because the shape has a very high RMS, and consequently you have high losses as compared to just the DC passing through the current. Now obviously if you go to much higher capacitor or higher frequency, you can get lower values, but then it becomes impractical. Okay, so the basic switched capacitor converter with the flying capacitor has a fairly high conduction losses. These are conduction losses. I'll talk about switching losses later on. Now, a way to remedy this is to convert this circuit into a resonant switch capacitor converter. And this is done by adding an inductor. If you are, of course, switching at the same resonant frequency, the switching frequency has to match the resonant frequency, then you have a sinusoidal current passing here through this, now let's call it tank, like Google is calling it, it's a resonant circuit. And then there are two advantages here. Number one, which we can understand, is that we'll be switching at zero current switching. It's really not solving the switching losses. But another characteristic of this circuit is that the RMS here is lower than the RMS of the exponential current that we have seen. Okay, so this is a real benefit. So we can actually reduce the conduction losses. I'm not talking about the switching losses, but the conduction losses. To understand this, let's have a look now at the situation of a hard switch system that is with no inductor, just capacitor, and the resonant. And again, the question is, which one of them has the highest RMS? And if the RMS value of this resonant here will be lower than the RMS of the exponential curve, then we are actually gaining something. So here is an empty spice schematics that is modified for resonant operation. And then what we are expecting to see, if the switching frequency matches the resonant circuit, we are expecting to see here a half sine wave here during the charging, half sine wave here during the discharging. And otherwise, the operation is basically the same. That is, the the general behavior is very similar to the basic switch capacitor converter, except that the waveforms are sinusoidal. So here is an approximate analysis of what we can expect. Now the power loss will be a function of the resistance in the circuit, which will be RDS1 plus the ESR and ESL of the capacitor of the inductor, in fact, and then IRMS square, and then the model itself, the losses are the equivalent resistance and the average current coming out square. So by comparing this to this, I can actually obtain this value. So now the average related to the peak, since it's a half a sinusoidal waveform, is 1 over pi. RMS is I peak over square root of 2. And here I'm getting the relationship between the RMS and the I average. This is trivial. And then, assuming that the total resistance is the RDS on ESR, I'm taking one RDS on because I'm assuming a full cycle of the sinusoidal waveform. Half is one resistance and the other one is the other resistance. So this is like one RDS on, and ESR actually should be here also ESL, which I've not written here. This is the total resistance in the resonant branch. And then comparing these two, I'm getting that this is the resistance, total resistance, times pi square over 2, which is about 5. So the penalty here is not that high, as we've seen earlier. It is not dependent on the capacitor or resonant frequency. Obviously, if you go to low frequency, then you'll have a large inductor, a large capacitor, and then you might have for the inductor a larger ESL. But basically, it is independent on the frequency and capacitor. It is only dependent on the total resistance. Now, of course, at high frequency, the resistance of the inductor will change because you'll have an RAC. I'm not going into this detail, just to show that indeed using a resonant switch capacitor converter is easing the loss issue and actually lowering the conductance losses. And here is a run of this circuit. This is this circuit now. And what we see here is the resonant current in the resonant branch. This is the voltage of the capacitor, which is sinusoidal here. And here I'm showing the drain to source voltage of one of the transistors and the current of this transistor. You see very nicely here, zero current switching. Again, I'm not now discussing this issue, but rather that the fact that it is sinusoidal and it looks really very nice. However, if I want to be more realistic, I have to replace the ideal switches with MOSFETs, and here I have MOSFET, and running it again, the same circuit, only that I have here MOSFET, and running it again, I see basically similar result, except that the transistor now has very high spikes at the turn on and turn off. And the reason is that in zero current switching, you are still left with switching losses due to the output capacitance of the transistor. So during this switching instant, you are actually charging or discharging these capacitors, and so the energy stored in this capacitor is now dumped into the transistor, and we see here these spikes due to the high current resulting from the current of this capacitor when charging and discharging. So zero current switching does not solve completely the issue of switching losses. In this presentation, I'm not going to discuss other solutions. There are other solutions to this same circuit that we are going to discuss, the Google switch tank converter. There are advanced circuits that actually converted to a zero voltage switching operation, zero voltage and not just zero current. And by this, the switching losses can be reduced. Again, in this presentation, I'm not going to discuss it. just to alert you that to the fact that zero current switching is not the end point. You'd like to do better than that. Now, zooming in here, we see very nicely the sinusoidal part here, but then at the switching point, we have these high spikes. So now that we have this background of switch capacitor converters and resonant switch capacitor converter, we can go and analyze the circuit of Google that was presented in this paper. This is one version. There are other versions, and this particular case is 4-to-1. There are other, of course, topology for different ratios. And what I'm going to do is just to go into the circuit and explain all the operational steps. Now, the best way to explain it is really to start from output and going back to the input, although, of course, in reality, the input is affecting the output. I'll talk about it in a minute. So we have here two types of control, S1 and S2. All the S1s are working together, like S2 and S2 here are working together, and S1 and S1 are working together. So starting from the output and assuming a steady state, we see that during the S2 duration, these two switches are on, okay? And you see that the capacitor is in parallel to the output. So therefore, the steady state, the voltage on the capacitor will be close to the output voltage. I'm already showing here the voltage, the steady state voltages of the other capacitor that we'll see how they being generated in a second. Now during S1, this transistor is on and this transistor is on. And what we see here is that, and this transistor is on, and what we see here is the output now is being connected through this capacitor, charged to V out, and actually connected in parallel to this capacitor, which is grounded. Now this is V out plus V out, so we have here 2 V outs. So it's in steady state, this will be equal to 2 V out. Then we go to the next stage. Again, S2 is on, S2 is on, and then S2 is on, and we see that we are connecting this capacitor, which is charged to twice V out, plus the input in parallel to this capacitor, connected here to ground. So therefore, the voltage across this capacitor at steady state will be 3 V out. And finally, this 3 V out is added to the input, and it is connected in parallel to V in. So V in is 3 V out plus V out, and therefore V out is 1/4 of V in. So it's a 4-to-1 step down converter. Very clever. A very important feature of this converter, which I'm not showing in detail, but it could be understood, I think, very easily, is that the voltage of any of the transistors is not larger than 2 V out. This is very important. You see, we have a V in, which is 4 times V out, while the voltage on the transistors is only twice V out, that is half V in. Now, since the RDS on is really a function of the maximum voltage of the MOSFET, the lower the stress, the lower the voltage, the maximum voltage required for the MOSFET, the lower will be RDS on. So this helps to get transistor with lower RDS on. This is a very, very nice feature of this particular configuration. Now, in the original paper that described this topology, there is an experimental part. A unit was built and tested, and actually there is a picture, and then there's also a thermal image of the board. And here, just a summary of some key results. One of them is the efficiency, of course, which we are very much interested in. This is a 650 watt converter, 48 volt input, 4-to-1 transfer ratio. And you see, let's forget about the blue one. The red one is going up to 99, very high. And then at the point of, say, 650 watts, it's about 275, which is not too bad. Now, as I've said, this is just the very, very first version, and there's been some modification. I'll talk about it in a minute. And then there is a loss distribution here. So what we see here is that most of the loss is the conduction of the MOSFET. Switching is very small. And then we have the losses of the inductor. And this is the wire and this is the core, I guess. Capacitor and the copper traces of the circuit. And there's some driving losses for the gate. So it looks very, very nice. And this is, in my opinion, a very, very impressive contribution of the Google Power Electronics team. So since that time, there have been many modifications which are showing zero voltage switching, and the topology are modified to operate in a little bit different way. Of course, we have now GaN transistors available, and so this also can reduce the loss. So it seems that this approach is really viable, and there are some indications that it's going to be implemented in many practical circuits. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.